So feature selection and feature engineering is the first step of the data analysis, and also is the most important part, because it means if you don't have good features in the beginning of your analysis, if you don't have good model of the data, it means that you actually fail the task. I think that with 99%, your analysis, future analysis, will be non-useful. So what is feature? Feature is some meaningful characteristic of the object which we analyze. Yes, and the feature engineering is another topic which doesn't seem to merit any review paper or books, or even chapters in books, but it's absolutely vital to machine learning success. Much of the success of machine learning is actually success in in engineering features that a learner can understand. And this phrase is key phrase for today's topic. And just look to this phrase. So this understanding that your features is more important, that future analysis, future selection of method to analyze your data, it's really key to success. Feature engineering solves some problems. When your goal is to get the best possible results from a predictive model, you need to get the most from what you have, from data what you have. This includes getting the best results from the algorithms you are using. So you just select the best hyperparameter of the model. In case of clustering, you're trying to find the best number of clusters and something like this. It also involves getting the most out of the data for your algorithms to work with. My favorite example is pregnant women. When we're trying to predict is some woman pregnant or not, you may select a lot of features how to classify your group into pregnant and non-pregnant. You may select hair color. Yes, it's also a characteristic of the woman, but it doesn't reflect pregnancy at all. Yes, you may select some, I don't know, size of clothes. It may also be useful for analysis because pregnant women will be bigger in general than non-pregnant, but it also could not reflect the property of pregnant women. Yes, and something like this. So you need to find the best representation of your, the best way to represent your data structure and data properties. So how do you get the most out of your data for predictive modeling? It's a really question which you need to ask yourself every time you start doing something with your data set, or when you don't have data set and you need to create data set with the using of your database. So feature engineering is creation of features, it's construction of features. It's really important step. The features in your data will directly influence the predictive models you use and the results you can achieve. You can say that the better the features that you prepare and choose, the better the results you will achieve. It's of course it's true, but a little bit misleading. The results you achieve are a factor of model you choose. Model, it means model of clusterizing or classification model, and the data you have available and the features you prepared also. So it's like combination. Even your framing of the problem and objective measures you're using to estimate accuracy play a part. Your results are dependent on many interdependent properties. So results, not a straight line how to achieve the best results. You need great features that describe the structures inherent in your data. So it's your aim as data analyst. Better features means flexibility. What does it mean? It means that you can choose some wrong model or less optimal and still get good results. Most models can pick up on good structure in data, and the flexibility of good features will allow you to use less complex models that are faster to run, easy to understand, and easy to maintain. And this is very desirable because when you're trying to construct deep neural networks with hundreds of artificial neurons, it's not a good solution when you have problems inside your data set, when you have garbage in. So it's better to construct feature analysis, simple, straight line, how to separate your classes if you have linear separability. It's the best solution. So better features means simpler models. And with well-engineered features, you can choose the wrong parameters less than optimal and still get good results for your model for much the same reasons. You do not need to work as hard to pick the right models and the most optimized parameters. So you save your own time when you create good features. You don't waste your time in order to find the optimal parameters for model. And with good features, you are close to the underlying problem and a representation of all the data you have available and could use the best characterize that underlying problem. So you may express your problem in a better way. And better features means better results. So feature engineering is the process of transforming raw data into features that better represent the underlying problem to the predictive models, resulting in improved model accuracy on unseen data. So you see that you have some raw data. For example, a lot of information from patient in the hospital. You have results of laboratory tests. You have results of some ultrasound diagnosis, MRI images, something like this. A lot of information. And you want to select the best, the most meaningful from this raw data set. And of course, feature engineering is a little bit, we may say that it's an art. That mastery of feature engineering comes with hands-on practice and study of what others that are doing well are practicing. So you need to practice in feature engineering in order to be master of this art. So one more time, what is a feature? When we are talking about tabular data, it described in terms of observations in rows that are made up of variables and attributes in columns. So an attribute could be a feature. Attribute, characteristic, same thing. And the idea of a feature separate from an attribute makes more sense in the context of a problem. And feature is an attribute that is useful or meaningful to your concrete problem. And it's an important part of an observation for learning about the structure of the problem that is being modeled. We use meaningful to discriminate attributes from features. So you need to separate these two terms. Attribute, it's some information about data set, hair color for women, and feature, which is meaningful for our analysis. In computer vision, an image is an observation, but feature could be a line in the image. In natural language processing, a document or a tweet could be an observation, and a phrase or word or word count could be a feature. So you just perform some transformation of your raw data set in order to obtain this feature. In speech recognition, an utterance could be an observation, but a feature might be a single word or phoneme. Yes? So you extract feature from your data. The whole process of machine learning consists of several stages. You have some tasks. Before, you're starting with data selection, integrate data, then normalize into data set, collect it together. So you collect your data from several sources, from several storages in one data set, big data set. You pre-process your data, you format it, clean it, delete some wrong observations, sample it so you can work with it. So you prepare your data set for future analysis. You transform your data, and feature engineering happens here. You need to transform your raw data set into some updated data set with features instead of attributes. And create models, evaluate them, and tune them. So the process step we may divide into two parts: the process itself and data transformation with feature engineering. Yes. After that, we perform some model, evaluate the efficiency of this model. If this efficiency is not enough for us, so for example, we need to construct a more accurate model, we may return to the previous step with data preprocessing, data transforming, and to change something in our data structure in order to improve the model. After that, we again evaluate the model efficiency, analyze is it enough for us or we need something more, transform our data one more time and do it several times before we don't get the good results. So that feature engineering is a process of feature creation, extracting features from our raw data. Feature extraction, the automatic construction of new features from raw data. The key word is automatic construction. Some observations are far too voluminous in their raw state to be modeled by predictive modeling algorithms directly. Common examples include image, audio, and textual data, but could just as easily include tabular data with millions of attributes. For example, when you open your Facebook, you have your news from your friends, and this page construct automatically in the base of your likes, activity, your interests, and Facebook analyze a lot of information about your activity in Facebook services to prepare this web page with news for you. So it's also tabular actually data. And feature extraction is a process of automatically reducing the dimensionality of these types of observation into a much smaller data set than that can be modeled. So we need to simplify our data set. For tabular data, these might include projection methods like principal component analysis, which you are familiar with, and unsupervised clustering methods. So you see clustering methods are also about a reduction of our data set. For image data, this might include line or edge detection. So when you select only edge of your objects, depending on the domain, image, video, and audio observations lend themselves to many of the same types of digital signal processing methods. Key to feature extraction is that the methods are automatic. Also, may need to be designed and constructed from simpler methods and solve the problem of unmanageably high-dimensional data, most typically used for analog observations stored in digital formats. So we just do it automatically in order to reduce the feature space. Feature selection is a step that goes after feature engineering step. We created a lot of features, 100 for example, which we think are meaningful for analysis. We think that they are meaningful, but how to prove this meaningfulness? We need to select and rank all our features in case of influence to the future model. So for many features, we go to few number of features which are useful, and we need to prove this usefulness. So not all features are created equal. Some of them are most important, some of them less. And those attributes that are irrelevant to the problem need to be removed from the analysis. And there will be some features that will be more important than the others to the model accuracy. And there will be also be features that will be redundant in the context of other features. Feature selection addresses these problems by automatically selecting a subset that are most useful for the problem. Feature selection algorithms may use scoring methods to rank and choose features such as correlation. Correlation, the most popular method when we calculate correlation between the feature and predictive value, for example, class label or something else. So your target value. A correlation or other feature importance methods. Actually, feature discriminant analysis allows you to estimate G-value, its linear separability of classes using the features. So you may also rank your features in accordance with this parameter. More advanced methods may search subsets of features by trial and errors, creating and evaluating models automatically in pursuit of the objectively most predictive subgroup of features. So if you have a good computer with fast speed of calculations, you may just create several subsets of features and evaluate the model, classification model, for example, a lot of times using different subsets and select the best subset from the from all. You construct a model using 2 features, 3 features, 4 features, 5 features, and so on. Save the value of accuracy that you have here, and after that, select the best subset. There are also methods that bake in feature selection or get it as a side effect of the model. Stepwise regression is an example of an algorithm that automatically performs feature selection as a part of the model construction process. Regularization methods like lasso and retrogression may also be considered algorithms with feature selection baked in, as they actually actively seek to remove or discount the contribution of features as part of the model binning process. So stepwise regression and lasso allows you to automatically rank features in order in with the rank of usefulness or influence to your model. And the problem that feature selection solves that feature selection methods aid you in your mission to create an accuracy predictive model. They help you by choosing features that will give you as a good or better accuracy whilst requiring less data, because it's really good to create more simple, the simplest model you may perform. Feature selection methods can be used to identify and remove unneeded, irrelevant, and redundant attributes from data that do not contribute to the accuracy of a predicted model or may in fact decrease the accuracy of the model if you have some noisy attributes. Fewer attributes is desirable because it reduces the complexity of the model, and a simpler model is simpler to understand and explain. Explainable models, it's new way now in your mainstream. We are trying to construct not black box, but some explainable model for human beings. As for filter selection algorithms, let's look to some groups of these methods. The first group is filter methods. Filter feature selection methods apply a statistical measure to assign a scoring to each feature. The features are ranked by the score, some score, for example, Fisher criterion value, and either selected to be kept or removed from the dataset. The methods are often univariant and consider the feature independently or with regard to the dependent variable. Some examples of some filter methods include the Chi-square test, information gain, and correlation coefficient score. So, for example, you may take two variables. First will be some feature number one, and the second variable will be your target value. You calculate correlation coefficient and save it. Repeat it for the second feature and your target value, save it, and score all your features using this coefficient. But the problem that using several score methods, we will obtain different results, and it's difficult to compare them and make some conclusion about the best features. Filter methods are generally used as a preprocessing step. The selection of features is independent of any machine learning algorithms. Instead, features are selected on the basis of the scores in various statistical tests for their correlation with the outcome variable. But actually, in this case, when you calculate some statistics, it will be parametric estimation, and you may have some problems if you have normal distribution. Yes, so you need to take it into account. Wrap methods. It's not a group of feature selection algorithms. Consider the selection of a set of features as a research problem where different combinations are prepared, evaluated, and compared to other combinations. A predictive model is used to evaluate a combination of features and assign a score based on model accuracy. So these methods use not only data itself, but data in combination with some model. For example, if you solve some classification task, you take your classification model, you take your data, and trying to evaluate it on several subsets of features. The search process may be methodological, such as the best first search. It may be stochastic, such as random hill climbing algorithm, or it may use heuristics like forward and backward passes to add and remove features. I prefer forward passes features when you estimate accuracy of your model for each feature, firstly. So you train your model using only one feature number 1, feature number 2, feature number 3, and calculate n accuracies. After that, you select the feature which gives you the best accuracy and add it to your list, best features, yes? After that, you add to this best feature pair all other features, and you train your model again using 2 features. As actually, again, select the best accuracy. It will be the best feature number 2. And after that, you repeat it with all your features. An example of a wrap method is a recursive feature elimination algorithm. Also, in wrapping methods, we try to use a subset of features and train a model using them. Based on the inferences that we draw from the previous model, we decide to add or remove features from your subset. The problem is essentially reduced to a search problem. These methods are usually computationally very expensive. So it's a really expensive methods when we are talking about time, because we try a lot of hundreds and maybe thousands of combinations, and it costs something in case of computational activity. Some common examples of wrapped methods are forward feature selection, backward feature elimination, recursive feature elimination, and etc. So forward selection is an iterative method in which we start with having no feature in model. In each iteration, we keep adding the feature with which best improves our model till an addition of a new variable doesn't improve the performance of the model. It's I said about it before. Backward elimination. In backward elimination, we start with all the features and removes the least significant feature at each iteration, which improves the performance of the model. We repeat this until no improvement is observed on removal of features. And recursive feature elimination, it's greedy optimization algorithm which aims to find the best performing feature subset. It repeatedly creates models and keeps aside the best or the worst performing feature in each iteration. It constructs the next model with the left features until all the features are exhausted. It then ranks the features based on the order of the elimination. So we also rank it using your model. We may use decision trees in order to rank the model in their importance, and a lot of techniques. On the best way for implementing feature selection with wrapper methods is to use Baruta package that defines the importance of the feature by creating shadow features. Shadow features, new term. Oh, pardon. And it works in the following steps. Baruta package. Firstly, it adds randomness to the given data set by creating shuffled copies of all features, which are called shadow features. Then it trains a random forest classifier. Forest decision trees. It's a classifier which allows us to create a tree with the rules in nodes, and it's compare some feature. If this feature greater than 5, for example, it will be red class. When it's feature less than 5, it will be blue class. So force classifier on the extended data set and applies a feature importance measure. The default measure is mean decrease accuracy to evaluate the importance of each feature, where high means more important. At every iteration, it checks whether a real feature had a high importance than the best of its shadow feature. Whether the feature had the highest z-score than the maximum z-score of its shadow features, and constantly removes features which are deemed highly unimportant. Finally, the algorithm stops either when all features get confirmed or rejected, or it reaches a specified limit of random forest runs. So you compare your features with some shadow features which were created automatically. It's artificial features. And also, I think that last group of methods, embedded methods. They're alone which features best contribute to the accuracy of the model while the model is being created. The most common type of embedded feature selection method are regularization methods. Regularization methods are also called penalization methods that introduce additional constraints into the optimization of a predictive algorithm, such as a regression algorithm that bias the model toward lower complexity, fewer coefficients. You know that fewer coefficients is really, really important for us. Examples of regularization algorithms are lasso, elastic network, and rich regression. It's embedded method. It's something that include in your model, and it's automatically improve the quality of model without your impact to it. It do it automatically. Embedded methods combine the qualities of filter and wrap methods. It's implemented by algorithms that have their own built-in feature selection methods. Some of the most popular examples of this method are lasso and rich regression that have inbuilt penalization function to reduce overfitting. Overfitting, it's a process when your algorithm just train on your data set, on training data set, and it doesn't describe some general tendency in your data, but it remember only this particular data set. It's really, really problem for many methods. Lasso regression performs L1 regularization is not really clear for you now because you don't familiar with neural networks and logical regression. So just you may look to this slide and understand that there is something which allows you to perform to get the best performance in your model. So the main differences between the filter and wrapper methods for feature selection are just like a result of just comparison between these two groups. Filter methods measure the relevance of features by their correlation with dependent variable, while wrapper methods measure the usefulness of a subset of features by actually training a model on it. So please understand this difference. Filter methods are much faster compared to wrapper methods, as they don't involve training the model, because training process takes some time. On the other hand, wrapper methods are computationally very expensive as well. Filter methods use statistical methods for evaluation of a subset of features, while wrapper methods are cross-validation. So you just check efficiency of your model in different subset of data. Filter methods might fail to find the best subset of features in many acquisitions, but wrapper methods can always provide the best subset of features, so you always have some best result. Using the subset of features from the wrapper methods make the model more prone to overfitting as compared to using subset of features from the filter method. So you may select the best subset, but it provides overfitting. Of course, the best instrument to find the best features is a Python. You have a lot of packages in order to play with your dataset. In particular, scikit-learn, SciPy allows you to find the best features without you don't need to spend your time writing the code. You're just using methods which gives you this opportunity to pass something into function and analyze the results. But of course, you may play with these packages in Python, and we will work with Python next year. We'll have discipline advanced methods and tools for biomedical data analysis, when we will talk about neural networks, decision trees, something like this. You will have practical tasks and lab works in Python, but you could not use it without clear understanding what are you doing. And it's a problem of the present time, because there are a lot of instruments how to play with data, but many of data scientists and data analytics works with data without understanding what do they do. So I want you to be sure that when you perform some function in MATLAB, in Python, that you understand what underlie this process. So feature selection is really important step in data pre-process, and I want to focus you. I want to ask you to think about features when you construct some algorithm, and do not miss this step. Do not go to constructing some super complicated algorithm without analyzing data set you have. So that's all about feature engineering. Do you have any questions? No questions. Okay.